that last time. So a reduced row echelon form for a 2 by 2 matrix looks like this, right? 0, 1, 1, 0, 0, 1, a vertical, and then question marks. And the question marks would have been the solution of the system. But reduced row echelon form not always looks like this, especially if you have 3 variables but 2 equations. So in this case, it would be 2 variables, 2 equations, right? But here's a special case. Special case, let's call it A. And then we'll have special case part B and C and so on. So a special case part A is a case where you might have this kind of reduced row echelon form. So you have 1, 0, -3, 5, 0, 1, 5, and 7, right? So, and we know that the first column, these are the coefficients of variable, let's say, x1. These are the coefficients of variable x2, and these are the coefficients of variable x3 in 2 different equations. So we have 3 variables, but we have only 2 equations, not 3 equations, right? So the reduced row echelon form, which is this, looks kind of odd because you have the diagonal 1, the only number below this diagonal is 0, but the numbers above it are not necessarily 0. You have a 0 here and then -3, 5, and on the other side are the constants. So this is a special case. Okay, so let's see what this means in terms of interpreting a solution for this system. Well, whenever you have this type of a special case, this has infinitely many solutions. And in this case, depending on variable x3. So depending on variable x3. So let's see what this means. Well, just remember, once you have this system, you can rewrite it in terms of its original variables. So let's write the original equation using the bottom row. What do we have? 0 times x1 is just 0, so x1 drops out. 1 times x2, we're going to have x2. 5 times x3 is 5 times x3 equals 7. And this is just from these numbers. We can rewrite the original equation like this. Now, x2 can be written in terms of variable x3. So let's solve for x2 in terms of variable x3. There we have it. So in this case, notice that x3 is left to be anything. And as soon as you pick a value for x3, then x2 will have a new value. So in this case, we say the variable x2 depends on the value of variable x3. Now let's do the same thing for the row above this in the system. So we're going to do the same thing for this row. This time we're going to do, so 1 times x1 is x1. 0 times x2, 0. So there is not going to be an x2 in this equation. Negative 3 times x3 will be negative 3x3 equals 5, which is the constant on that side. So let's solve this equation for x1 in terms of x3. So we'll have x1 equals, move this to the other side, 3x3 plus 5. So now we've been able to solve this system in terms of variable x3. So we have x2 equals that, x1 equals that. The question is, what is x3? Or what could x3 be? X3 is free to be anything. To be any value. So instead of having a single unique solution for the system, because this is a special case, we have infinitely many solutions depending on variable x3. So how would we represent the solution? The solution, instead of saying x1, x2, x3, it would be equal to, x1 is going to be equal to that, so 3x3 plus 5, comma, right? That's our x1. x2 is going to be that equation, that whole equation, minus 5x3 plus 7, comma, and x3 is going to be x3. So this is the solution of that system, which depends on x3. And so let me add. So this is infinitely many solutions depending on the value of x3. Okay, so that's one of the special cases. Let's look at another special case. So this is another kind of a special case. I mean, it's pretty much like part A, but it looks different. The reduced row echelon form looks different. And that's, so a special case, let me say B, not A. We just went over part A. So it will look like this. We'd have 1, negative 3 halves, 5 halves, and then 0, 0, 0. Okay, so this is two equations, two variables. So this would be the coefficients of, let's say, variable x1. The second column would be the coefficients of variable x2. And the far right numbers will be the constants. Okay, so this, notice that this bottom equation simply means 0 equals 0, right? This equation does not contradict anything. So it does not contradict anything, right? 0 is always equal to 0. So from this, the bottom equation means that x2 is free to take any value. It's the second row, and first row gives us the value of x1, especially because we have this diagonal 1 already figured out from the reduced row echelon form, right? So that's the interpretation of the bottom row, that once again, it's because x2 is free to take any value, then we have infinitely many solutions. So then from the first row, let's write the original equation. 1 times x1 is x1. Minus 3 halves x2 is minus 3 halves x2 equals the constant on the other side, which is 5 halves. So let's solve this equation for x1. x1 equals, move the x2 term to the other side. It becomes positive when you do that, plus 5 halves. So that's the solution for x1. And x2, we already know it can be anything. So once again, this system, this special case, has infinitely many solutions. I'll move this up a little bit. Depending on the value of x2, right? Because it's x2 that is free to be any value. From the bottom equation, we interpret that. That's the interpretation of that statement. So x2 can be anything. Okay, so the solution of this special case would be that it has infinitely many solutions depending on the value of x2. How would we write it? So x1 comma x2 would be equal to, x1 would be this whole thing, so 3 halves x2 plus 5 halves comma x2. So you pick x2 to be any value, you'll have a different solution. That's why we have infinitely many solutions depending on the value of variable x2. Okay, let's see another special case. So we'll call this a special case part C, right? In this case, we're going to have a special case for a 3 by 3 matrix. So the regular, just recall, this is from section 2.2. Recall that a regular or normal reduced row echelon form looks like this. Looks like this. So it's 1, 0, 0, and then the question mark on the far right, 0, 1, 0, 0, 0, 1, and then we have. So that's what a reduced row echelon form would normally look. But with a special case, we have, it might look like this. Here we have we have 1, 3, 0, 0, 0, 1, 4, 0, 0, 0, 30. And recall that these would be the coefficients of variable x1, coefficients of variable x2, and coefficients of variable x3. So we used the Gauss-Jordan method apparently, and we ended up with like this, a matrix like this. So this is a reduced row echelon form. Now, in this case, if you carefully look at the bottom equation, it's basically telling us that 0 is equal to 30, right? 0 on this side equal to that constant on the other. And this is impossible. So this is impossible. That's impossible. And therefore, this system has no solution. Okay, so that's a special case which leads to this final conclusion. Okay, let's look at another special case, and we'll call this special case part D. Okay, suppose we did the Gauss-Jordan method and we ended up with a matrix like this, with a reduced row echelon matrix like this. So 1, 0, 6, 0, 1, 2, 0, 0, 0. Okay, so in this case, note what is happening. We have two variables. Let's call this x1 and this one x2. We have two variables, two columns on the left of this. These are the constants. And we have three equations. So we have more equations than we have variables. And that always leads to this kind of a special case. So the bottom row is telling us that 0 equals 0. And we can't argue with this, right? 0 can be equal to 0 at all times. So this equation does not contradict anything we already know. Now let's move up one more row to the middle row. That one is telling us that x2 equals 2. There's not going to be any x1 from this row. x2, 1 times x2 is x2 equals 2. So x2 equals 2. The very top row is telling us that 1 times x1, x1 equals 6. So in this case, even though it's a special case, we actually do have a solution. And the solution is 6, 2. It's a unique solution. So we have a unique solution, which is that. What role does the bottom row play in all this? The only role it plays, it's not contradicting anything, any solution that we have. So that 0 equals 0 is not contradicting this. So that's okay. And then the unique solution is 6, 2. Now that we've introduced these special cases, let's see a couple of examples of systems that may lead to a special case. Okay, suppose we want to solve the following system using the Gauss-Jordan method, i.e. and that's the other name for it, right? The elementary row operations. Okay, so here's that system. We have 6x plus y equals 8, x minus 3y equals minus 5, 2x plus y equals 2. So I strongly encourage you to, at this time, pause the video, go back to your own scratch paper, solve this as best as you can. It doesn't matter if your solution is going to be wrong or not. It doesn't matter. Important is that you first solve this before looking at my solution. Then once you're done, come back to the video and see how I did the solution, and then you can compare this with what you have. Okay. I'm assuming that you've done that, and now you have your own solution in front of you. And so let's get started here. The first thing is, of course, writing down the augmented matrix, which would be 6, 1, 8, 1, -3, -5, 2, 1, and 2. Okay, so recall that the Gauss-Jordan method works based on getting a 1 in that corner, right? So we would expect to, or let me write it here, although this is a special case, so I'm going to, and then we're going to have that, something like that. So this is going to be what we are, this is our objective. We are here, we want to go to that point. By the way, this is the vertical, that's that side, right? We are here, we want to move to that. Okay, so the first thing is we want to get a 1 in that corner. Fortunately, we have a row that has a 1 in that column. We can simply move it. We can interchange row 1 with row 2. So interchanging row 1 and row 2, we're going to be able to get the 1. So we have 1, -3, -5, and then 6, 1, 8, and then of course row 3 stays where it was, 2, 1, 2, right? So recall that our objective is to sweep column by column, get each of these columns first, and then move to the next column, and repeat with the 1 in that other, in the next column. So we're not done with this column, right? We have the 1, but the 6 and 2 have to be converted to zeros, right? Remember that from section 2.2? So at this point, let me ask you this. Which row is the pivot row? Okay, I hope you said row 1. Row 1 is the pivot row. The question you might have is why? It's because we just got the diagonal 1 in that row. So row 1 contains the diagonal 1 we just got, which is row 1. So this becomes the pivot row. So this is important why, and I'm repeating what we talked about in section 2.2, because we should use this row, the pivot row, to convert the 6 and 2 to zeros. So let's do that. So row 6 is in row 2. So we're changing row 2 according to this operation. How are we going to get a 0 in that spot? Well, all we need is add a -6 to this, and we're going to get a 0. But where is the -6 going to come from? It's going to come from multiplying the pivot row by -6, -6 row 1, plus row 2. That's going to give us a 0 in that spot, and we have to then do the same thing to all these numbers in the other columns. So how are we going to get the 2 converted to 0? Well, all we need is to add a -2 to this, and we're going to get a 0. But where is the -2 going to come from? It's going to come from multiplying the pivot row by -2 and adding it to the third row. So let's do that. Row 3 is equal to minus twice row 1, which is the pivot row, plus row 3. So these are the 2 row operations that will help us convert the 6 and 2 to zeros. All right, let's do that. Again, I'm assuming you've done all this and you're just comparing my solution with the one you have. If you haven't, please complete your solution and then come back to the video. Okay, 1 minus 3 minus 5, and then I'm going to do this operation first. Minus 6 times 1 is minus 6, plus 6, 0. Minus 6 times minus 3, it's positive 18, plus 1, positive 19. Minus 6 times minus 5, that's positive 30, plus 8, that's positive 38. We're done with this. Let's move down to the next row operation. So this is saying multiply the row 1 by -2 and then add it to row 3. So let's do that. -2 times 1 is -2. +2, 0. -2 times -3, +6. +1, 7. -2 times -5, +10. +2, 12. So now compare this with this one, with the reduced row echelon form. Compare this with that. Are we done with the first column? Absolutely, we're done with the first column. So now we need to convert this column to those numbers. And in each column, we start with the number that has to be converted to 1. Then we worry about the other numbers that have to be converted to 0. So let me write it here so we can look at it as I scroll up in a moment. I'm just copying that down. Okay. So now, in the second column, and by the way, so this is the vertical. In the second column, the first number to obtain is convert 19 to 1. Then we're going to worry about what to do with the -3 and 7. How are we going to convert 19 to 1? Well, when you obtain the diagonal ones, always multiply the row by a number that would get you the 1 in the spot where you're looking for that. So in this case, we need to multiply the second row by 1 over 19, right? So let's do that. So row 2 is equal to 1 over 19 times row 2. Okay. Doing that, we're going to get this next matrix. Right? 1 over 19 times this, we get 1. 1 over 19 times 38, we get 38 over 19, which is 2. And then 0, 7, and 12. Okay, so now our objective is to convert the -3 and 7 to zeros, right? Well, let me ask you this. Which row is the pivot row now? Have you thought about that? It has to be the second row. This is the pivot row. Why is that? Because the diagonal 1 that we just got is in the second row. So now this is important because we need to use this pivot row to convert the -3 and 7 to zeros. Let's do that on the next page. Okay, so to convert this -3 to 0, all we need is a +3 to add it to this, right? So where is this +3 going to come from? It's going to come from multiplying the pivot row by 3 and adding it to row 1. So row 1 is equal to 3 times row 2, which is the pivot row, plus row 1. How are we going to get 0 in this spot? All we need is a -7 to add to this 7 and to get 0. Where is the -7 going to come from? It's going to come from multiplying the pivot row by -7 and adding it to the third row. So row 3, which is the row we're changing, is equal to -7 times row 2 plus row 3. Those are the two row operations for us. Okay, let's carry out this row operation. With this, we have 3 times row 2 plus row 1. So 3 times 0 is 0, plus 1 is 1. 3 times 1 is 3, plus negative 3, 0. 3 times 2 is 6, plus negative 5 is 1. Second row, we can write it as it is. Third row, negative 7 times row 2 plus row 3. So negative 7 times 0 is 0 plus 0, 0. Negative 7 times 1 is negative 7 plus 7, 0. Negative 7 times 2 is negative 14 plus 12 minus 2. So we've achieved the reduced row echelon form. There is no more columns for us to go through on the left side. These are the constants. Okay, so what is the interpretation of this special case? Well, the bottom row is telling us that 0 on the left equals negative 2. Is that possible? No. So because of that, because this is impossible, so it's not possible, then this system has no solution. So we can say no solution exists. And we stop there. Okay, let's have a look at another special case. We want to solve this system, x plus 2y plus 3z equals 5 minus 2x plus 6y plus 4z equals 0, right? So notice that we have 3 variables and 2 equations. So right there, there's a clue to you that you have you're going to have a special case here. Okay, so let's write the augmented matrix. And again, I'm hoping that you pause the video at this juncture, do your own work on this, and then come back to the video to see what I've done. Okay, so I'm assuming you've done that. This method, Gauss-Jordan method, begins with the augmented matrix. In this case, the augmented matrix is 1, 2, 3, 5, and then minus 2, 6, 4, and 0, right? So ideally, this is what we're looking for. We're looking for 1, 0, 0, and question mark on the other side, then 0, 0, question mark on the other side. This is what we're aiming for. This is our objective, to convert this to that. Let's see if we're going to be able to do it. Okay, the first thing, we're sweeping column to column, right? Notice that the first column, we already have a 1 in this corner, right? So the next thing for us is to get the 0 in that column, this one. So right now, the pivot row is our first row. So this is the pivot row, because row 1 contains the diagonal 1 we need in that spot. Okay, so all we need to convert this negative 2 to 0 is a positive 2, so we can add it to this and get 0. But where is the positive 2 going to come from? It's going to come from multiplying the pivot row, or row 1, by 2 and adding it to row 2. So we're changing row 2, so row 2 is equal to twice row 1, which is the pivot row, plus row 2. Okay, so let's carry out this row operation. Two times row 1 plus row 2. 2 times 1 is 2, plus negative 2, 0. 2 times 2 is 4, plus 6, 10. 2 times 3 is 6, plus 4, 10. 2 times 5 is 10, plus 0, 10. Okay, so now compare this with this reduced row echelon form, which is our objective. Did we get the first column done? Yes. This column looks exactly like that. So now we move to the second column. In the second column, remember please from section 2.2, in each column, we first get the diagonal 1. So we need to convert this 10 to 1 before we worry about converting the 2 to 0. So how do we get 1 in this spot? Very easy. We multiply this whole row by 1 over 10. So let's do that. Row 2, because 10 is in second row, right? Row 2 is equal to 1 over 10 times row 2. And let's write down the next matrix. One over 10 times 0 is 0. 1 over 10 times 10 is 1. 1 over 10 times this 10 is 1. 1 over 10 times this is also 1. Okay. So let me see if I can still bring that into a screen. Yes, I can. Compare this with this matrix. We already got the 1 in the second column. We're here, right? We're in the second column. We got the 1. Now we need to worry about converting the 2 to 0, right? Okay. So before we do that, let me ask you this. Which row is the pivot row at this point here? If you answered row 2, you are correct because we just got the diagonal 1 in that row, right? It's in the second row. So that's the pivot row. Okay. So and that's important because we need to use the second row to convert the 2 to 0. How are we going to go to do that? Well, all we need to convert this 2 to 0 is add a negative 2 to it. But where is the negative 2 coming from? Well, it can come from multiplying the pivot row by negative 2 and adding it to the first row. So let's do that. So row 1, which is the row we're changing, right? Because the 2 is in row 1. Row 1 is equal to minus twice row 2, which is the pivot row, plus row 1. Okay. All right, so let's write the next matrix. Minus 2 times 0 is 0, plus 1, 1. Minus 2 times 1 is minus 2, plus 2, 0. Minus 2 times 1 is minus 2, plus 3, positive 1. Minus 2 times 1 is minus 2, plus 5 is 3. And the second row is just stays where it was. Okay, so now this is a special case because we have no more rows or diagonals to get, right? So we cannot proceed to the third column. So we have to stop here and figure out how to interpret this matrix. So this is as far as we can take our reduced row echelon form. Well, in this case, we have infinitely many solutions. And depending on, we started with x, y, z. So these are the coefficients of column or variable x, coefficients of variable y, coefficients of variable z. So we start from the bottom. We have, first of all, let me write down, we have infinitely many solutions depending on the value of z. Depending on z. So let's write down the solutions. Okay, so from the bottom equation or bottom row, we can write y plus z, right? 1 times y is y, 1 times z is z, equals 1, which is that. And then rearrange this, solve this equation for y. You have y equals 1 minus z, so that's the solution for y, variable y. Then how about from the top row, we can write 1 times x is x. 0 times y is 0. We're not going to write that down. 1 times z is positive z equals 3, which is on the other side, right? So solve this. Let's solve this for x in terms of z. So x equals 3 minus z. So that's the solution for variable x. Okay, so now what is the final solution going to look like? We were supposed to have some numbers, right, for x, y, z. But because this is a special case, instead we're going to have x like that. So 3 minus z, comma, y is going to be equal to 1 minus z, and z is going to be z. It's a free agent. Z can be anything. So that's why we have here, we say we have infinitely many solutions depending on z. I wrote it on the other page, but it's okay. Let me also add it here so it's complete. So infinitely many solutions depending on z. So z is free to be anything. You can pick z to be negative 10 or 0.03 or positive 100,000, anything, right? Whatever you pick for z, it'll give you another different solution. So we have infinitely many solutions. And I hope if you have questions about this, please post them right underneath the video on the discussion board. All right, so we've done a few examples of special cases. Now, before we wrap up this section, let's do another example of the regular kind, not the special case, but the regular kind, just to make sure that we remember what it's like to solve a regular system, right? So this is just an additional exercise to what we did in section 2.2. So we want to solve, or using elementary row operations, i.e. the Gauss-Jordan method. Using that, solve the following system. Okay, so we have 2x2 plus x3 equals negative 2, 3x1 plus 5x2 minus 5x3 equals 1, 2x1 plus 4x2 minus 2x3 equals 2. Okay, so I'm really hoping that at this point you pause the video, do your own work on scratch paper, and then come back. And hopefully our answers agree. And if that's the case, you've got this method very well. Okay. So I'm assuming you've already done that and you have your own solution in front of you. So the beginning of this method is with the augmented matrix. Notice that we have 3 variables here, x1, x2, x3, x1, x2, 3, but the first equation is missing x1. We cannot skip any coefficients, so because there is no x1, I'll have to put a 0 instead, and then 2, and then 1. And then, of course, the constant value. Then we have 3, 5, negative 5, 1 on the other side, which is the constant. Then lastly, 2, 4, negative 2, and then, of course, the constant on the other side. Okay, so this is the augmented matrix. Now, this is interesting because let me quickly write down what our objective is. Our objective is to obtain this reduced row echelon form, right? To go from here to that. Okay, so we're going to need a 1 in this corner, but it's a 0. So if it was, say, 4, I would multiply that whole row by 1 over 4 to get a 1 in that corner. But with 0, what can I do? It won't be useful if I multiply this by 1, right? I'd still get a 0. So we must interchange row 1 with one of these two rows. Either interchange it with row 2 or interchange it with row 3. But which one? Well, if you look at row 2, if you interchange row 1 with row 2, you're going to get you're going to get a 3 in that corner, and then to get a 1, you'll have to multiply that whole row by 1 over 3. And that's going to create fractions, 5 over 3, negative 5 over 3, and 1 over 3. These are fine. I mean, these fractions are not really awkward. They're small, nice fractions still. I mean, it's not a fraction like 17 over 35 or 12 over 49, something like that. It's not one of those types of bigger fractions. It's a small fraction. So we should be able to handle it without wasting a lot of time. But let's see what happens if we switch row 1 with row 3. If we do that, then we're going to end up with a 2 in that corner. And then to convert the 2 to 1, we're going to multiply that whole row or this row by 1 over 2. And when we do that, we will not end up with fractions. So it's better, you can interchange row 1 with either row 2 or row 3, but it's better if you interchange it with row 3, because you're not going to get the fractions that you would get if you interchange row 1 with row 2. So let's do that. So we're going to interchange row 1 with row 3. As a result, we're going to get this. We're going to get 2, 4, negative 2, and 2. And the bottom row will be 0, 2, 1, negative 2. And of course, the middle row, which didn't move, is 3, 5, negative 5, and 1. Right? Okay. So now we can do what we need to do, which is convert the 2 to 1. Right? This is our objective. We want to get from here to that. And we go column by column. So we need to, in each column, we obtain the 1 first, then we worry about the zeros. So I need to convert the 2 to 1. Let's do row 1, which is the row we're changing, equals 1/2 times row 1, right? So the next matrix then, the next matrix will be 1. Let me do this so you can see what I'm doing, and then I'll remove the other page. So 1/2 times row 2 is 1. 1/2 times 4 is 2. 1/2 times negative 2, negative 1. 1/2 times 2 is 1. The second and the third row stay as they were. Like that. Okay, so now we have to keep this in mind, right? That what our objective is. This is our objective. We're moving every step, we're moving from here to that. Okay, so now with the first column, we've got the 1, we've got this 0. All we need is convert the 3 to 0, right? So let's do that. Let me ask you this. Which row is the pivot row at this point? If you said row 1, you are correct, because row 1 contains the diagonal 1. So pivot row, or the current diagonal 1 that we just got. Okay, so to convert the 3 to 0, all we need is add a -3 to it. But where is the -3 going to come from? It's going to come from multiplying the pivot row by -3 and adding it to row 2. So because we're changing row 2, 3 is in row 2. So row 2 is equal to -3 times row 1, which is the pivot row, plus row 2. Okay, so the first row is not changing. Now -3 times row 1, -3 times 1 is -3, plus 3, 0. -3 times 2 is -6, plus 5, -1. -3 times -1 is +3, plus -5, it's -2. -3 times 1 is -3, plus 1, -2, and the row 3 stays as it was. Okay, so compare this with this matrix, right? We're done with the first column. So now we need to move to the second column. In each column, remember, we obtain the diagonal 1 first, then we worry about the zeros. Okay, so right now we have -1, but we want a 1 there, right? How are we going to obtain that? Very easily. We multiply the second row by -1. Let's do that. Row 2 is equal to minus row 2. Okay. And I'm going to write this down again so we have it in front of us. So I'm doing this so you all can see what our destination is, which is this red matrix or the reduced row echelon form. But you should have this in your mind all the time, right? As you go through the Gauss-Jordan method, this is what your objective is. So we just got, in the second column, we just got the diagonal 1. What does that mean? Remember what does that means? That means that the second row, the row that contains the diagonal 1, is the pivot row. And that's important because it means to convert these 2's to 0, we need to use the pivot row. Okay, so how are we going to get a 0 in that spot? Well, all we need is to add a -2 to this, and we're done. We got to get a 0 there. Where is the -2 going to come from? It's going to come from multiplying this row by -2 and adding it to that 2. So row 1 is equal to minus twice row 2 plus row 1. The same thing with the other 2, this one. How are we going to get this to be 0? The same thing. We need a -2 to add to this. Where is the -2 coming from? It's coming from multiplying the second row by -2 and adding it to row 3. So row 3 equals because this 2 we're changing is in row 3. So row 3 equals minus twice row 2 plus row 3. Okay. So let's do that. Let's carry out these operations. I'm going to do this one first. So minus twice row 2 plus row 1. Minus 2 times 0 is 0 plus 1, 1. Minus 2 times 1 is minus 2, plus 2, 0. Minus 2 times 2 is minus 4, plus minus 1, minus 5. Minus 2 times 2 is minus 4, plus 1, minus 3. Okay, so now let's do this row operation, which is multiplying the second row by negative 2 and adding it to row 3. So minus 2 times 0 is 0 plus 0. Well, meanwhile, let me write down the pivot row, which I almost forgot, 0, 1, 2, 2. Now we're going to do this row operation. So minus 2 times 0 is 0 plus 0, 0. Minus 2 times 1 is minus 2 plus 2, 0. Minus 2 times 2 is minus 4 plus 1, minus 3. Minus 2 times 2 is minus 4 plus minus 2 is minus 6. Okay, so now compare this what we have, with this one, with reduced row echelon form. Did we get the second column? Yes, we just got it done. So now we move to the third column. In the third column, which number should we convert first? It's the number that is going to be converted to 1, right? That one. And then we worry about the zeros. So to do that, what row operation do we need? All we need is to multiply this row 3 by a negative 1 over 3. So row 3 is equal to minus 1 over 3 times row 3, and that's going to give us a positive 1 in that spot. Let me do that on the next page. Okay, so the first two rows don't change. Now this one, multiply this whole bottom row, row 3, by negative 1 over 3. So we have negative 1/3 times 0, 0. Negative 1/3 times 0, 0. Negative 1/3 times minus 3, positive 1. Negative 1/3 times minus 6, positive 2, right? So compare this with what our objective matrix is, which is that one, right? So we just got the diagonal 1 in the third column. Now we need to convert the 2 and negative 5 to zeros, right? Which row, let me ask you this, which row is the pivot row now at this point? It is, if you answered row 3, you're absolutely correct. Why row 3? Because it contains the diagonal 1, the current diagonal 1 that we just got. So this is the pivot row. And why is that important? Because we're going to use the pivot row to convert the 2 and negative 5 to zeros. Okay, to convert the negative 5 to 0, what do we need? We need to add a positive 5 to this, right? But where is the positive 5 going to come from? It's going to come from multiplying the pivot row by 5 and adding it to that. So row 1, which is the row we're going to change because of this negative 5, is equal to 5 times row 3, which is the pivot row, plus row 1, which is the row we're changing. Okay, to convert the 2 to 0, all we need is, this one. To convert the 2 to 0, all we need is a negative 2 to add to this and get 0. Where is the negative 2 going to come from? Well, it's going to come from multiplying the pivot row by negative 2 and adding it to the second row. So row 2, which is the row we're changing, is equal to minus twice row 3, which is the pivot row, plus row 2. All right, so now let's carry out this operation. We have, first I'm going to do this, 5 times row 3 plus row 1. 5 times 0 is 0 plus 1, 1. 5 times 0 is 0 plus 0, 0. 5 times 1 is 5 plus negative 5, 0. 5 times 2 is 10 plus negative 3, 7. So now this row operation. Minus twice row 3 plus row 2. Minus 2 times 0 is 0 plus 0, 0. Minus 2 times 0 is 0 plus 1, 1. Minus 2 times 1 is minus 2 plus 2, 0. Minus 2 times 2 is minus 4 plus 2, minus 2. And then the third row is the pivot row, so it stays as it was, like that. Okay, compare this matrix with this matrix, with that one. Are we done? Yes. The left-hand side is the reduced row echelon form. So this side is going to be the solution of the system. X equals 7, y equals negative 2, z equals 2. So let's write it down. So x comma y comma z equals 7, negative 2, comma 2. Okay, so that is the final solution of that system. Please make sure you go through these examples first without looking at my solutions, and then come back to the video to compare your solution with this. And that way you will learn all this material in a solid way, which guarantees you a top grade in the course. And the more of this practice you do, the better you will get at this stuff. Okay, so this wraps up our discussion of the special cases plus a regular example we just did. And next time when we come back, we will talk about section 3.1. So I bid you a very nice day and see you next time.